So yes, thanks, Russell. So yes, today I'm going to talk about Riak Ensemble, and actually the interesting part about Riak Ensemble, as you'll soon find out, is Riak Ensemble actually doesn't build on Riak. It's a separate thing we built to add strong consistency to Riak, because adding strong consistency to an existing code base is hard. It's actually good to have a much smaller, built-from-scratch library that you can test and build from the get-go to actually provide the guarantees you want. But we'll talk a little bit about that. So what is Riak? Oh yeah, and yeah, I'm Joe at Basho, but also I'm JTuple on the internet. Many of you may or may not follow me, but I'm JTuple on Twitter, on GitHub, IRC channels, and so forth. So if you follow me, this is me. Hi. So anyway, Riak Ensemble is a paxos-based framework for scalable consistent systems, and we'll talk about what that is in this talk. But before we do that, it's useful to understand sort of the motivation. What's the problem we're trying to solve, and you know, why are we ending up at where we are? So of course, in Erlang, we know Erlang makes it very easy to build distributed systems, scalable distributed systems. So in this case here, we have 8 nodes. Because of the actor model, you can have the same communication pattern for local actors, which are the little blue boxes in this picture here, or remote actors, and Erlang just works. It's easy to scale this to 60 nodes, 32 nodes, 128 nodes, whatever. There's some communication things you run into in the end, and there are people working on that. But in general, you can scale, at least for shared nothing kind of systems where message passing works for you, which is great. The problem, of course, is what happens when you have state, right? What happens when you have shared state? Well, crap, shared state is not a shared nothing problem anymore. It's a shared problem. And so most of you, I imagine, and most of us in general, when you want to solve this problem, end up using a database, right? You might have a set of nodes, in this case here 4 Erlang nodes that implement your app. You have a database behind it. Maybe it's a single node database. Maybe it's a really cool, awesome, scalable database like Riak, which in this case here is also written in Erlang, great, and scales to 8 nodes here. And that works well. And this is what most of you probably do and should do, build things on top of databases that someone else is handling the scalability problem for you. The problem is this always doesn't work, right? What happens if you're actually writing a database? What happens if you're me? We can't make Riak better by adding a database to Riak. Otherwise, just use the other database that Riak is using, right? That makes no sense. Also, what happens if, and this isn't just a database, any other kind of thing you might want to build too, a messaging system or any kind of infrastructure component, always using, oh yeah, we're going to bring in an external database component, may not always be the right idea. And of course, what happens if it is small state, right? A lot of application are just small amount of metadata, configuration information, things like that, data in the kilobyte to megabyte range. You don't really want to then say, oh yeah, you need to install this heavyweight database just to manage my 150K routing table consistently. That's a little silly. So it would be nice to have an embedded database library that you can use. And of course, Erlangers would say, hey, that's what Manija does, which is true. Manija is a thing that's built into OTP, which allows you to do that. The problem is if you build a lot of application on Manija, and there are plenty out there, you'll eventually run into an error that looks like this, which basically says, here's the deal. You had a network partition. It leads to a split brain scenario. Both sides of the network partition allowed writes to occur. Manija then sees later, gee, I have 2 inconsistent views of the world. What do I do? And now there are things that were added later in OTP where you can set settings to Manija that say, okay, fail writes if there's not a majority of people connected. That's not fail-proof. There are still corner cases where you'll still run into this scenario. Fundamentally, why does this occur? Well, it's because of the CAP theorem, which you probably heard Basho people talk about before. But the CAP theorem, it's an acronym, CAP. It's consistency, availability, and partition tolerance. And fundamentally here, the theorem says you can have 2 out of 3. And in the real world, unfortunately, network partitions are a reality of life. Even if you have the best network equipment, that doesn't prevent a janitor coming in and unplugging a wire. Network partitions can occur, and when they occur, you have a split brain. And so the whole concept behind CAP here is that you really only have a choice between building systems which are always consistent but not available during a network partition, so-called CP systems, and systems which are always available but are inconsistent during a network partition, like AP systems, which Riak today is one of those. And you pick one. Now again, neither of these have to do with high availability, right? Both of these scenarios can be highly available. You can build a highly available system that can tolerate node failures, 3 out of 5 nodes failing, and still be up and be consistent. There are plenty of systems that do that. Riak Ensemble does that, as we'll talk about. But the issue is during a network partition, you won't be available because a node being offline is actually an easier thing to handle than a node being online and not being able to talk to anyone. That's the harder scenario. So just to illustrate this real quick, because this talk isn't really about CAP, but there's a simple scenario here where we have 5 nodes. And in this case here, nodes 3, 4, and 5 are the primary owners for some set of data we care about in this example. And we have 3 clients trying to read or write this data. So in the case here where everyone can talk to everyone, both AP and CP systems are totally fine. Everything works. The world's happy. But let's say we have a network partition now. And for those who aren't quite familiar with what I mean by network partition, think about if you're on IRC and you see a net split, right? And suddenly half the group goes away and then later people come back. That's just servers not being able to communicate to each other. So in this scenario here, let's say nodes 4 and 5 can't talk to nodes 1, 2, and 3. Well, in a CP system, you can't let both sides succeed here because one side would be inconsistent. So only one side gets to succeed. In this example, in most systems, it's going to be the right-hand side here, because it's the side with the majority of the replicas, which in this case here were 3, 4, and 5, so 4 and 5. But again, as far as the clients on the left-hand side are concerned, your database is unavailable, right? It's not highly available as far as they're concerned. They try to access the database and are told, sorry, database unavailable. Try again later. Okay. Whereas an AP system, like Riak, for example, works just fine in this partition. It even works fine if there's 2 partitions. It even works fine if you're very unlucky and you're in this scenario where you have 4 partitions. But again, what you're given is consistency, right? A write that occurs by the client talking to node 1 is not going to be seen in the reads that the client talking to node 5 does, at least not right now. Of course, eventually, the partitions will heal, and eventually the data converges, which of course is eventual consistency. And the whole idea behind eventual consistency is basically what I just said there, but to make that concrete, imagine a scenario where you have a value that's currently A. You do a network partition, and we update the value on 2 sides of the partition. One side sets it to B, the other side sets it to C. Okay, that's inconsistent. But what happens when the partition heals? Well, what happens here is you end up just merging the values, and then your future reads sees both values. That's a little interesting, and that seems kind of odd if you're coming from a consistent world. But there are a lot of people who do build apps on Riak that can handle that, because there's a lot of classes of applications that are actually very tolerant of this. Generally, these 5 types of applications. Applications where you only write your data once, you never have conflicting writes, because it's fundamentally, by definition, impossible. Applications where your data is immutable or idempotent, it doesn't matter, because every time you write a value, it's the exact same value you're writing. And so even if it conflicts, you can just pick any of them. They're the same value. So those are straightforward, and a lot of content systems are that. There are cases where you can just, in your app, maybe just pick the last one, the most recent one, or pick a random one. That works fine, too. And of course, there are cases where you might have business rules, where it is just up to you. We give you all the values, and you pick one because you have business rules that can choose that. Maybe your most valuable customer is the one who gets to seat on the airplane, not the other guy. Okay. And then also, there's a lot of research out there to build eventually consistent data types. Someone earlier in this room mentioned CRDTs. I think it was in Chris Michaeljohn's talk, which is a set of data types you can build on top of eventually consistent systems, in which for a period of time the data diverges, but eventually it converges to the exact same values it would have had if you updated everything sequentially. These are like counters and sets and maps. There are ways to build those where, while they are temporally divergent, they always converge to the correct count. And so because of this, Riak works really well for a lot of systems. The problem is there's a lot of apps which aren't one of these 5 cases, or maybe they're 95% of these 5 cases, but they still need some strong consistency. And today, what a lot of people will do is they won't use Riak, or they'll use Riak and tie it into Postgres or MySQL or whatever. And so what we wanted to do at Basho was add both of these, add AP and CP to Riak. And again, as I said earlier, we chose to do that by building a separate library that provides CP and then integrating that into Riak. And that's Riak Ensemble. So there's the motivation. Let's actually talk a little bit about Riak Ensemble now. Actually, before we do that, let's talk a little bit about consensus algorithms. So the whole problem of strong consistency or any consistent system really comes down to distributed consensus. You have multiple actors in a system, multiple replicas, and you want them to agree upon the state of the world. And as far as consensus algorithms are concerned, there's 3 main categories. Now, there's a few minor ones too, but there's quorum consensus algorithms, there's chain replication, and there's virtual synchrony. We're going to talk about quorum consensus algorithms today, because that's what Riak Ensemble uses, and that's what most systems use in the world as well, although there are some databases that use chain replication. Habari, for example, is an Erlang database that actually uses chain replication for consistency. And Hyperdex is another one that's not written in Erlang that does. And so as far as quorum consensus is concerned, most of you have probably heard of some of these before, but there's 3 main quorum consensus algorithms. There's Paxos, there's the Zookeeper Atomic Broadcast Protocol, and then there's Raft, which is fairly new. And of course, I said on slide 2 of this whole talk that this is a Paxos-based framework. So obviously, where we're going. We're going to be going to Paxos. But we'll talk about Paxos, but we'll talk about the other guys in a minute too, just briefly. And so Paxos, right? Paxos is sort of the granddaddy of distributed consensus algorithms, quorum-based consensus algorithms. And a lot of folks talk about Paxos being complicated, and Paxos can be. And there are interesting parts of Paxos that can be that we'll talk about in a few slides. But very simple, trivial Paxos is actually not that complicated, at least theoretically. It becomes complicated in implementation, but it's not too hard. In fact, here's an entire slide that shows you the sequence diagram for basic Paxos, which would be nice if I animated this, but oh well, I'll just use a nice little pointer here. Yay. So here's the deal. The idea behind Paxos, what's really interesting, is Paxos is a state-based or a value-based consensus algorithm. The idea here is you're trying to agree upon the state of a single value. And so what you do here is you have 3 nodes in this case. It could be 5 nodes, it could be 7 nodes. Usually it's an odd number of nodes that you're going to use, and we can talk about why later. But in this case here we have 3 nodes. And node 1 here wants to change the state of the system. And so what he's going to do here is he's going to go ahead and he's going to increment what's called the ballot number. In this case here, it's n, because n is shorter than ballot number. And he's going to increment the n, and he's going to send this value to all of the nodes, which includes himself. So in this case here, himself and nodes 2 and 3, with a prepare message. And what those nodes are going to do here is when they get this prepare message, is they're going to compare that number to the highest known ballot number they've ever seen. If this is higher than any value they've ever seen, they're going to accept this. And they're going to send back a promise to node 1 with 2 things, saying, here's the ballot number you just gave me, and here's the current value I have for this value or this state. And if node 1 gets back a reply from a quorum of nodes before it times out, then he can proceed. If he doesn't, then the request fails, and you give up, or maybe you retry. That depends on the particular system you're in. But fundamentally, you go back to step 1, re-increment the ballot number, and continue on. But assuming this eventually succeeds, you move on, and node 1 decides what the next value should be. And he can pick whatever he wants. Usually, though, it's some function of the values he got back. He picks the most recent value, and then from that applies some modification function to it and knows what the new value is. But this could have just easily been that this was a request coming in from a client that says, hey, set the value to 10. In which case, he's going to ignore the new values anyway and just say the new value should be 10. But it doesn't really matter. Anyway, node 1 picks whatever he wants. It's his choosing. And then he sends a commit message back to all the other nodes and says, hey, commit this value. And here's the ballot number, again, that we agreed upon earlier. And again, at this point in time, if all of the nodes still haven't seen a ballot number higher than that, and it's coming from node 1 again, everyone accepts it. They write the value. The nodes send back an accept. And if you get a quorum of accepts back, then you know that the system is consistent, and there is you've wrote this value. That is the current state of the value as far as the quorum is concerned. And you can reply back to the client or whatever the system is running on top of this and say, hey, the current value is vn, whatever I just wrote. And again, if this fails, if you didn't get a quorum back, the request fails, and it's a failure or a timeout, however you give that to your users. So okay, Paxos is kind of straightforward. I mean, there's some implementation details here, although a lot of the implementation details are harder in Java or C, right? In Erlang, you can implement a basic Paxos diagram like this with a couple gen FSMs, run on some nodes, and boom, you have a little prototype Paxos thing that you can hammer out, and it kind of works. So that's kind of cool. The interesting part here, though, is you do this for every single request. It's a whole round trip. And the problem with that is it's 2 round trips per request. First round trip to do the prepare, second round trip to do the commit. Which isn't too bad, but it turns out you can do better in most real-world systems. And that's where multi-paxos comes in, which is an optimization. And the idea here in multi-paxos is if you have a case here where you're going to have the same node propose multiple values over time, then you can have a long-lived ballot number, which we generally call epochs or terms when you're talking multi-paxos. And so you can skip the first round after you at once. So there's 2 phases. Phase 1 where you establish a new term, and then all the subsequent phases where you reuse the existing ballot number from before. So to show that briefly, on the first request, we do exactly what we just did a minute ago. It's the full 2-phase, prepare, promise, commit, accept. Except we've changed just a little bit here now. There's now 2 things that matter. There's an n, which is still the ballot number, and then there's the I, which is a sequence ID. So when you want to start a new phase, a new round, a new epoch, we increment the ballot just like before. We set the sequence to 0, and we do the full prepare, promise, except now we're providing the n and the I instead of just the n. And then again, we do the same thing before, but we're providing both the n and the I now in the later stages down here. But again, this is what we just talked about effectively before. The difference here, though, is that for each additional request, we reuse the same n that we already agreed on. And so we're not going to increment that anymore. And so we can actually skip the prepare phase. And we only need to increment the sequence number and directly do commit and get the act back. And as long as it's still node 1 with the same n, with an I which is higher than the previous I, everyone accepts it. If any of those conditions are wrong, then people will not accept it. You won't get a quorum response. You fail. Node 1 is no longer the leader for this particular epoch. Someone else will eventually come along and restart back at the phase 1, where they'll re-increment the ballot number, which will again establish a whole new epoch that is logically higher than any request this node could have done. Again, in a well-behaved system where no one's lying, which is we're assuming here. So that's multi-paxos. Now again, details, but this is a 40-minute talk, so that's about what we can do on the high level here. But it's pretty straightforward, right? 2 slides. Here's the way you can do quorum consensus. Why do people talk about Paxos being hard? Well, it turns out the main problem you have here isn't the details. The main reason why people usually make it hard is because integrating Paxos in real systems leads to some challenges. The main challenges in database systems, oh, sorry, real quick. We'll talk about, that's 1 round trip, by the way, in the common case, duh. We just saw that, so that's why it's great. Anyway, the problem is that shipping the entire state is expensive. Your state is big, right? So for cases we're talking about metadata, routing tables, that's great. But what happens if your state is a database? You know, you're using paxos for your database, and you can't ship your entire database around each time. That would be a gigabyte, a terabyte, petabytes. That would be silly. And so using pure direct value-based paxos to do consensus over a database has always been a problem. People don't want to do it that way. So what do? Well, they change it from using paxos to directly agree on the value of the database state to using paxos to implement a replicated state machine, where instead what you're doing is you're basically doing a replicated log of commands. And you're agreeing upon each consensus round on which command should be at a particular point in the log, effectively. And so that everyone is coming to a consensus on the sequence of commands, in which case if you apply all of those commands independently on all the nodes, you get the same state. Okay, that makes some sense. Obviously, high-level hand-waving here a little bit. If you want more details of that, the little paper I can show you in a second. The problem is when you go and do that, you end up with a lot more problems now, because this is actually hard. Because now you have to deal with a whole lot of failure scenarios. So the nice thing about the paxos thing we talked about before, pure state-based paxos, is a node can go offline for years, or have its data deleted, or be partitioned. Whenever it comes back, it only needs to go through one full round of propose, commit, accept, and it has all the state, because you always provide the state each time. But when you move to a system where you're using paxos and a log, the log you're not shipping around each time. You're shipping around just the most recent thing, and so you have to implement all these other things on top of that system that deal with log recovery. So there's various issues. There's log recovery. Log recovery is an issue where a node is missing some entries in its log, and you need to figure that out and bring it up to date. There's log trimming, which is the case where a node actually has entries in its log that no one else agrees should be there. Well, you need to identify them and roll them back. There's also the fact here that your log can't just run forever. You'll eventually run out of disk space, so you periodically need to roll it up. You need to snapshot it. Well, you need to deal with how does that fit into your whole scenario here. And there's a lot of challenges with that. And there's a paper that Google wrote, Paxos Made Live paper, very many years ago, which actually talks about most of these, although they leave out some interesting tidbits which are still exercised to the reader. But you can certainly go and look at that paper and see sort of, hey, even Google found this really, really hard. And so that's what people reference when they say Paxos is hard, because doing that is really, really hard, and doing it right is really hard. The good news is a lot of other smart people realize, hey, the problem with this too is that there's no formal proof of any of this working. It's sort of, hey, the only thing we really have is Google wrote something and it kind of worked for them. Awesome. So the better way to do this might be to actually build the whole notion of log-based replication into your protocol. And that's actually where the other protocols I mentioned earlier come into play. Zookeeper and Raft both do that. They're actually formal proofs which are effectively a consensus system which is very similar to Paxos, tied to a log replication system where they're both part of the core protocol. They're not, here's Paxos plus the separated log that we sort of tie together. And there's still a little more slight differences between it, but conceptually you can think of it that way. And of course, ZAP, the Zookeeper Atomic Broadcast Protocol, which is used in Zookeeper, which many of you probably know about. It's an Apache project in Java. If you want to learn more about that, I don't have any time to talk about it today, although I can offline. You can read the Zookeeper paper, or the other Zookeeper paper, or the other Zookeeper paper, or the other Zookeeper paper, and there's actually two others, and there's another one I think that's being published soon. So I have a lot of papers. Yay. One of the interesting things that's actually a very new paper is actually dealing with dynamic membership. So Zookeeper today has fixed membership. You have a quorum of 3 nodes. You can't ever add or remove a node later. There's a whole new paper on how you can do that. That's actually in Zookeeper 2.5, and will come out when Zookeeper 2.5 comes out. But it is on the development branch now. There's a paper for that too, which isn't up here. But there's a lot of really good research that shows, hey, we've formally proven a lot of these things. So that's one approach. If you do want to build a system and don't want to use what I'm going to talk about today, go look at Zookeeper. Of course, if you don't want to go look at the Java code of Zookeeper, you can also go look at Riak Zap, which is actually a port of the Zookeeper Atomic Broadcast Protocol that I did about 3 years ago to Erlang. It's 3 years out of date. We haven't touched it since. But you can at least see, hey, here's how you might implement this in Erlang if you were so inclined. And of course, there's also Raft. So Raft is the protocol that is another consensus protocol. It's just also similar to Paxos or consensus with a log. But its specific focus, it's the thing it's trying to solve, is being easy. In fact, the one paper that exists for it is called In Search of an Understandable Consensus Algorithm. Its whole point is to be easy to teach, easy to use, easy to build. And it actually is pretty easy. It came out about a year ago as far as this paper. And since that time, there's been an implementation of Raft in almost every language you can imagine. You can go to raftconsensus.github.io and find one. And if you care about one for Erlang, there's one called Rafter, which is actually written by a colleague of mine at Basho, Andrew Stone. And it's actually a pretty cool implementation. And you can go and take a look at that. So at Basho, we've tried Riak Zap, we've tried Raft, and there's different code out there in different qualities, and these are interesting things to go look at as well. So of course, all right, I've talked about all these. There's some interesting things, Paxos and logs. That's cool, and there's different ways to do that. You can do Paxos with logs, you can do Raft, you can do Zookeeper. But we're going to talk about Riak Ensemble now. I already told you earlier, Riak Ensemble is Paxos-based. Why? Didn't I just tell you there's a better way to do it? Shipping the entire state around is kind of crazy? Sure. It is entirely crazy if the thing you're trying to deal for your state is your entire database. If you treat your entire database as a single monolithic entity, Paxos doesn't work very well. You have to try the more complicated algorithms to do that. However, Paxos itself is fairly simple and fairly easy to write if that is something you can use. If you can just use state-based Paxos, it's a much simpler and easier to maintain code base. So it's in some ways a good thing to do if you can. And so what we ended up doing with Basho for Riak, and then what ended up being part of Riak Ensemble, is we realized that we can solve this in a different way, which is to focus on microstates. Oh, yeah, so here. Basically, the idea here is just make sure you have small states. And instead of having your database be one giant state, you just have your database be a bunch of microstates in which you're doing Paxos independently for each of these, which actually works very, very well for Riak because Riak's a key value database. The nice thing is this also solves a second problem. Remember how I mentioned this, a scalable protocol? It solves a scalability problem because the problem is that in traditional consensus, Raft, Zap, Zookeeper, it doesn't matter, the more nodes you add to your consensus group, well, the more reliable you are. You can have more and more nodes fail and still be up, which is awesome. But generally, after about 7 nodes, it makes no sense to add anymore. So usually you do 3, 5, or 7. You need an odd number so that you can tolerate up to F failures. So 2F plus 1 is basically what you want. So to tolerate 1 failure, you need 3 nodes. To tolerate 2 failures, you need 5 nodes. To tolerate 3 failures, you need 7 nodes. After that, do you really expect 4 nodes to fail all at once? Probably not. I mean, you can certainly go with 9 nodes. But you basically eventually run into asymptotic reason. For reliability, don't add more. So performance, though, right? A lot of distributed databases, you want to add more and more nodes to get faster. The problem is if you add more and more nodes to a single consensus group, the single consensus group gets slower. So you can't really add more and scale. On the other hand, if you're doing a bunch of separate, completely independent Paxos transactions of completely separate states, you can just add more and more nodes, which are part of completely separate Paxos groups, and you can scale it out that way by scaling out the number of sort of independent decisions you're making. Sure, that doesn't help you if you need to scale out, agreement on one value, but most real-world systems, right, scale on the data set size, not on everyone touching the one value over one name. And this fits well in Riak because, again, key value database, so each key is its independent state. And again, this doesn't have to be a key value database. You might think, no, but you said this is a generic thing. Sure. I mean, this could be used for, you could build a gen server on top of this. In fact, I had a prototype, I tried that, where your key is a PID, and the value is the state of the gen server, right? And what you do is instead of sending messages to it, you go onto Riak Ensemble, and the update function, which we'll talk about later, is actually just something that emulates like a gen server handle call, and suddenly have what looks like a scalable gen server. I mean, each independent gen server would be an independent Paxos group. So there's, this is somewhat generic, and key value, yeah, but key value, you can extend that in many ways. So of course, let's talk a little bit about the semantics of what this gives you. So what we're really focusing here is on conditional single key atomic updates. And again, this is single state, doesn't actually be a key, but that's just the phrasing we use here. And it's atomic, so it is atomic just the same as if you were doing a compare and swap kind of things on a CPU. It's the same level of atomicity we're guaranteeing here. So full serializability to a single key. Whoa, wrong button. Sorry, guys. There's a weird button that gets rid of the slideshow but doesn't bring it back. So you're watching the video. I'm sorry, technical difficulties. Okay. So anyway, so we have the single atomic updates here. And what this also means is basically a read, modify, write cycle, where the modify here is actually an Erlang function. So you apply an Erlang function, and what happens here is we actually get the most recent value that everyone agrees on. We apply the modification function to it, and we write it back. And so it's a consistent update to that, sort of a consistent read, modify, write. And of course, this function you have here can either return a new value or it can return fail. Generally, you can think of this as fail if a conditional, like for example, if a value is modified concurrently. So in Riak, for example, our modify function here is just checking a certain value that's passed in and seeing that if this value is changed, that means someone else concurrently updated the data. So it gives us sort of a conditional compare and swap property. But you could do other things here too. You could, for example, just always overwrite the data and never fail it if you wanted to. But it's fairly generic, get, modify, put kind of approach here. Of course, the design, so how it's actually built. So go back to multi-paxos. This is multi-paxos, simple multi-paxos per key. Of course, that means if we have 1 billion keys, do I have 1 billion complete separate independent consensus groups, all with separate leaders, all with separate pair and promise phases? You could. We don't. That probably doesn't scale very well. So the answer is no. What we do instead is we actually we group things together. We actually have some subset of consensus groups, and you partition your states across them. The nice thing is this is dynamic. It's entirely up to you to add consensus groups as you want. So, and by the way, consensus group is a large word, so actually we call them ensembles. which is hence the name Riak Ensemble. So we'll call them ensembles from this point on in this talk. But so you can have as many ensembles as you want, and you just say, hey, ensemble A owns these keys. It's up to you to decide how you do that routing as far as mapping keys to ensembles. Riak Ensembles mostly focus on creating ensembles and sending requests to them by ensemble key value. That's sort of your three things that you give it. And so again, each of these ensembles actually emulates the per key paxos. So how does that work? Well, there's two things we care about. There's epoch, there's the sequence numbers, and then there's the actual key value state. And so the ensemble itself actually handles the leader election, which is sort of the guy who becomes the main person who does the first round of paxos and stays the leader, and does subsequent requests for that ensemble. And so he elects the leader, he does the first round of paxos. The reason you have a leader election rather than just relying on the stuff I showed earlier is if you just rely on the stuff you have earlier without a leader election, without gating that, then you can have a bunch of nodes try to all become the new state. They'll all try to propose a higher ballot number. One will fail. You retry. Eventually, you might succeed, but you're going to get a lot of failures. So generally, what you do is you have some kind of leader election that gates it. The leader election isn't used for any safety guarantee. The paxos round, first round, guarantees you safety. The leader election is just designed to make sure that you, on high probability, don't have 5 nodes all trying to become the leader at once, or propose a new ballot at once. So they become the leader. They establish a new epoch that's doing the first round of multi-paxos that we talked about earlier. And they support the whole get modify put thing we talked about a minute ago. So to establish an epoch, it's what we just talked about. It's literally the first round of multi-paxos. That's what the ensemble will do. The key thing here is that different ensembles do this independently. So you might have ensemble A, ensemble B. Ensemble A will do this to establish the new epoch for that particular ensemble, for that particular leader, but a completely different ensemble would do this independently from that. These could be talking to different nodes or to different PIDs on the same nodes. It's concurrent. And you do this once to establish a new leader. Of course, and the state that we're agreeing with here is basically just that, the epoch, the sequence, the member, and the leader. That's the state that we're using during that multi-paxos transaction. And then, of course, we have the actual value associated with the microstates, the so-called key value objects, at least the parlance we use in Riak Ensemble. This includes the epoch, a sequence, and a key and a value, because again, this is paxos, right? Paxos, you have the epoch, you have the sequence, this is the n and the I we talked about earlier, and you have the key, that's just the unique name, and then we have the value, which is the thing we were passing around, the v in paxos. The idea here is this epoch and sequence are a sort of a subset of the epoch and sequence of the ensemble. So the ensemble, when it writes a value, writes the current epoch and sequence of that ensemble to that key. But in the future, when you read the key off disk, you're going to treat the epoch and sequence of that key to be what's stored in that key, not the value of the current ensemble. So you sort of are emulating the actual current state of this key is what's stored, not the actual live state. And we'll show that in a second. So to do a put, to do a write, to do a modify, whatever you want to call it, we do something that looks a lot like, this is for a key now. So this is how we emulate paxos on the ensemble. We do something that looks exactly, again, 2-round trip, looks very, very similar to multi-paxos here, the first stage of multi-paxos, but it's a little bit different. So the idea here is, let's say node 1 again is our leader. He's an ensemble leader now for a set of keys. And a request comes in that says, I want to modify key 5. Node 1 here is going to read key 5 locally, his local value off disk. And he's going to check the epoch of the key, of that object. And he's going to see, is this epoch older than the epoch that the leader, the current ensemble is? So perhaps the current ensemble is at epoch 5, the key you read off is at epoch 5. Or perhaps it's at epoch 4, from a previous leader who wrote it in a previous epoch. In any case, if it's before the current epoch, this basically means that this particular key is not current. It needs to go through the full 2-phase multi-paxos, just as if it was an independent paxos group, basically. And so what happens here is we do sort of what looks like the first round of multi-paxos. We send a get, we get a reply. The difference here is this get sort of is an embedded prepare, because these guys who are following this ensemble only reply to the get if they're still following him at his current ballot number. So there is sort of an implicit ballot number in here that's not shown. And they will reply back and say, yeah, you're our current leader, we're following you, here's my current state, here's my current object. And of course, each of these objects that come back, they have the value, but they also have the epoch that was part of those objects as well. And what node 1 will then do in that case is he'll pick the latest of all of those. So he picks the most recent value of all of those, he updates the epoch of that object to the current epoch, and he writes it back. And so this is effectively emulating the very first round of multi-paxos. This is emulating, the prepare, propose thing where you're establishing a long-lived epoch, but you're establishing the epoch per that particular microstate in that key by just realizing that it hasn't been done yet and doing it. The key here is you only do this the very first time this particular leader sees that key. If this leader were to go and do this again a second time, the request is going to look a lot like this. He's going to, look at it. It's going to, the object is going to be this current epoch. Great. So he doesn't need to do the first phase anymore to reestablish it. He actually just does the modification and does the write. Again, similar to the multi-paxos case of round 2, where you just have the single round trip. So we're emulating the same thing we did before, getting the same benefits we had before, which is, yes, you have 2 round trips in the worst case, but in the common case, in the case where node 1 stays a leader for forever, or a long time, weeks, days, it's 1 round trip in the common case. So again, what I just said. Gets are pretty straightforward. There's one thing to mention about gets I didn't put in the slides here, but one of the things we also do here is the leader here is actually we use a stable leader that establishes leader leases. There's actually details of a way to do that sort of in the Google Paxos Made Live paper. They do that as well in there. And so the idea here is that as long as there are folks following that leader, he remains the leader. So if someone else shows up and tries to say, hey, elect me the new leader, the other guy says, no, I'm still following this guy. You have to wait until everyone times out following from him before you can potentially ever elect another person. So the old lease has to time out first. This is slightly different than Raft. Raft doesn't have stable leaders. If someone shows up and says, elect me a new leader, he wins. That's how that algorithm works because it's a simpler design to do it that way. But anyway, the reason that matters is because that affects how gets work in just a second. So the first round of Git looks kind of like we just talked about. Again, you look at the current data. If it's from an old epoch, we have to do the full 2 rounds again. So we read, we refresh to get the object, we update it to the current epoch, we rewrite it. Again, we do that both for gets or puts to figure out what is the current state of that object. And then once we've done that, and keep in mind, we're actually writing here. We're doing a write on a Git because that's the only way to bring that object up to date at the current epoch. Again, it's basically the first round of multi-paxos emulated in the key state itself. So that's kind of weird, but again, do the full round, and it's not until after you've done the write and it succeeds can you actually return the value to the client. So a little heavy-handed, but again, you only do this once in the case where it's an old value. In the common case, the really nice thing here is that, yes, in theory, you would have to do a Git and do the 2 round trips. It would be 1 round trip. But since we're doing stable leaders, hence why I mentioned a few minutes ago, the current node actually has the correct value. The leader has the most recent value if the epoch matches. And so he doesn't need to talk to anyone. And so actually in the common case, he just returns and says, hey, I got the value. And so in the common case, reads don't talk to anyone except the local leader, which is actually even better than regular. So for example, regular Riak, we always need to talk to all of our replicas in the eventually consistent case. So this is an interesting sort of benefit here. And again, 2 round trips worst case, 0 round trips best case, which is really kind of cool. And at any point in time, if any of these round trips fail, you never get quorum, the leader will always abandon his leadership, which will cause a new leader to be elected, which will then increment the ballot number, which will increase the ballot number that everyone agrees to, which establishes a whole new set of sequence IDs that are larger than any previously written ID. And of course, that new leader will see on every new read or write operation that an object is from the previous epoch now. And so he will rewrite the object each time. And so that's how the new leader, after a leader change, sort of refreshes each object to the current state and resolves any ambiguity. So the way this is helpful, for example, for a partial write failure scenario, which I already mentioned here. So the partial write scenario here looks like something like this. So partial writes are an interesting thing that a lot of people don't think about in distributed systems. And particularly because you think, oh, ACID database doesn't have this problem. Like Postgres, if you were connected to Postgres master server over TCP, you can never get a partial write problem. The idea of a partial write is basically a write that failed that actually succeeded. So the database told you it failed, but then later on you read the value and it's there. And you think you can't have it with Postgres because Postgres does roll back transactions if the TCP socket disconnects during the transaction. That's true. But there are actually a really interesting race condition, even in Postgres, where you can hit it. Where Postgres does the transaction begin, it does the commit, it's definitely written now, and as it's sending that ACK back to your client, that's when the TCP link drops. You never see the packet, your client library says, hey, the write failed, but then if you go and read, you see the value. And so there's this interesting ambiguity of you don't actually know on failure, did it actually succeed or not? And the good answer is the next successful read you do will see it. And by the way, when I mentioned this in a talk a few years ago, someone said, that's not true about Postgres. Well, Kyle Kingsbury, if any of you know, AFER, he does a blog series on JSPN where he actually takes databases and does nasty things to them and see what they can do. And his series on Postgres actually shows that, yes, that's true. In this scenario, you can provoke a case where you get an unacknowledged write failure that actually succeeded. So you can do that. You can solve that by doing 2-phase commit to the client, but no one does that because it's dreadfully expensive. So in some ways, we always live with this partial write problem. The thing we want to do, though, is make sure the fact that once you do the future read, whatever you see, that's the truth and it never changes. So in a system like Riak, like today, eventually consistent Riak, there's a scenario where you can do a write that's unacknowledged. And so you don't actually know if the write succeeded or failed. And a future read you do shows the value being the old value. OK, fine. But then you wait a week and you read it, and it's actually the new value that you failed to write, which is sort of annoying. That's not a useful thing to build systems off of if you need the stronger guarantees. So the nice thing about this ensemble case here is that solves that problem. You get the better benefit, which is it can be either or, but the next read is the correct value. So here's how it works. So let's assume here that I have the value that's currently x, and it's at epoch 2. And I'm going to go ahead and write the value to y. And I wrote the value. Let's assume this network partition wasn't here originally. So I wrote it, and the value somehow got written to this side over here. So y got written on that side of the partition at epoch 2, but it didn't get wrote to these guys over here. It wasn't written to these guys. Now I'm going to go ahead and and of course, since it failed, I mentioned before, whenever you fail, the leadership is given up. It increments the epoch number or the ballot number, and so we'll now have epoch 3 is the new epoch that any future leader must have. No one can still be at epoch 2 and still be a leader. All right. So what happens? Well, let's say now we go into a read, and the read's happening on this side of the partition, okay? And so again, the answer right now, as far as the user is concerned, is the value could be x or y. I don't know. But what I care about is whatever I am told it is, it better not change again in the future. Okay, so what happens here is the user does go and read, and this time he's reading over here on this side, and he actually does a read. The reader does his local read. He sees that the value is currently x at epoch 2. Epoch 2 is before the current epoch we have here. Remember the refresh kind of thing. We check that it's older than the current epoch. So what do? We send a get to a quorum of nodes, which in this case here are these two nodes. They both reply back and say, oh yeah, the value is currently x at 2. And so the leader says, cool, x is the right answer. X wins. And so we rewrite x back at epoch 3, because that's the current epoch. So now we have x at 3, and we return x to the client. And so the user now sees x. It is x1, not y. The interesting thing here is there's still this y over here, but y is now older than x. It is not an older epoch. So in the future, when this partition heals, no matter what happens, you always will get a quorum which is at a higher epoch than this y. And so you effectively implicitly roll back this y. And so without even being able to touch the other side of the partition, we roll back y at the read time. And so we always cement x for all time as the correct answer. That partition value doesn't come back. Whereas in regular like Riak, you could see that value come back and win. Now again, we could have just as easily read y here and rewrote y at epoch 3. That's fine too. Again, the semantics are either x or y, but once it happens, you cement it for all time. So that's the semantics that Riak Ensemble gives you. So let's talk a little bit about the architecture real quick, how this is built. You're all Erlangers, so talk a little bit about process trees. So this is what Riak Ensemble's high-level process tree looks like. We actually have the app that then spawns a supervisor. And the supervisor has three things. Directly under that is a gen server called the Riak Ensemble manager. And then there's the Riak Ensemble peer supervisor and the Riak Ensemble router supervisor. Peers are basically the things which are part of ensembles. Those are the things that were node 1, 2, and 3 on all those things. They're actually PIDs. They're gen FSMs. And the router spawns router processes. Imagine that. These are gen servers, and the peer supervisor spawns these peers, which are gen FSM. So, standard OTP kind of app you would have here. So what is a peer? So a peer here, and so an ensemble isn't really a thing, it's a concept. There's a constraint. I have a notion of an ensemble, and this ensemble has some number of peers, 3, 5, 7, whatever. Again, ensembles are created dynamically, and I'll show you in a little bit how it's done. But what the ensemble is, it's a Riak KV ensemble peer. It's a set of those. Gen servers run either on one node or multiple nodes. And this is implemented in Riak Ensemble, the peer behavior. This does the whole multi-paxos emulator thing we just talked about. But what this peer actually also does is, because again, this is a scalable framework, is it actually has a backend. This is it's a behavior. It's a behavior you implement that says, okay, here's what my objects look like. Here's how I get input objects. Here's how I sync objects. There's a notion of sync, and then I kind of glossed over in this talk. And there's a few other things. Basically, you implement a backend, and that is how you connect sort of the high-level peer concept of ensembles and peers to whatever you want. You could build a distributed, scalable Paxos system on ETS, or you're building an ETS backend with this. And for Riak case, we actually have a special backend here, which basically interfaces Riak Ensemble with Riak, where you're actually having this thing which looks like sort of a separate database system actually storing data in Riak alongside all existing Riak objects in Riak's existing backend. But it can be, that's the thing you implement to attach this to whatever it is you're building. And again, it doesn't have to be an actual data store. It could be where this is actually like you're emulating gen server sends. And there's an interesting prototype. I should put some code up that shows how to do that. So I don't know how well it looks in the back, but real quickly, here's the behaviors you implement. So there's the callback init function, which just returns a state, just like you would do in gen FSM or gen server. There's a set of things called object accessors. So the objects, the things that we were passing back in values, the emulated, there was epoch, sequence, key and value. The value is sort of an opaque thing, right? Well, it turns out internally this is actually a single record we send back and forth, which has to contain all of those properties in it. It's up to you to use what you want, though. It's a blob. So whatever works for you. In Riak, we actually have our existing Riak object, which is that blob. But in your own system, you could have whatever that is. But what Riak Ensemble needs is Riak Ensemble needs to be able to access those four things. It needs to be able to get at the state. It needs to be able to get at the the key, the value, the epoch, and the sequence. And so you need to sort of implement things that just take in this opaque value and return each of those things. Likewise, you need to provide functions which, if we call them and just say opaque thing, opaque value, set it. And so you can set all of those too. So again, opaque as far as Riak Ensemble is concerned, implement those in your backend. Likewise, the get and put, these are the things which are the update the value. So get is retrieve the current value. Put is take this current value that you have and store it, whatever that means. Again, if it's an ets backend, you put an ets. If it was just a state in a server, you just say, okay, cool, it's in my server now. I'm done. And then there's this notion of syncing, which I'll skip over, but you can go look at the code. There's comments here. But basically, there's this notion of cases where you need to sync peers to bring them up to date, and there's some things you need to do if you want to implement that. And then there's this notion of ticking and pinging. So basically, periodically, the peers, the leader has a periodic tick, which is used in Riak Ensemble. This is where it does sort of its leadership. It extends the leadership lease. This is what it does in Riak Ensemble. We do parameterize that where you could, if you want to, also have it call back into your backend if there's something you want to do at a periodic interval on the leader. You don't have to implement this. This could just return OK, but it's there. Likewise, the nice thing about Riak Ensemble 2 is that this doesn't have to be a peer function. This whole backend could be something which then sends messages to an external process, like a gen server, and gets replies back. But if you do that, we need to be able to know if that external process is still alive. We can do monitoring, and monitoring we do. But there's cases, right, where there's a PID that's up, it's alive, but it's stalled, right? Maybe it's stuck on a backend, right, that for some reason it's taken a year, and you should just kill that PID or something, or your backend's running slow. And so we also have this notion of pinging. So periodically, we also send a message to that just basically calls a reply saying, yep, I'm still alive. And at any point in time, if a certain number of pings fail, we give up leadership, and we move on with life. So briefly, just talk about clustering, and then we're all done here for questions. So the idea here is internally, one of the things we deal with here is clustering. Like I said, membership's dynamic, so you can add or remove members, as we'll talk about, not just to nodes in a cluster, but also nodes per ensemble. So you can scale an ensemble from ABC to ABD, remove A. That's all built in. But there's also the notion here of dynamically creating ensembles. And one of the things we end up dealing with here is having to deal with some kind of cluster state, because in Erlang here, you want to be able to launch these nodes, join them together, and sort of have this cluster state propagate. And it turns out you can't easily do that consistently. You can do some of it consistently, but there's still some interesting failure scenarios where someone may not be part of an ensemble, but still needs to know who to go talk to. He still needs to see who should I talk to. And so we do that by gossiping this cluster state around periodically. And this cluster state basically consists of a notion of a node ID, the set of nodes. These are the nodes in the cluster that you gossip between, the set of currently known ensembles, and if you're enabled. And by the way, this is what it looks like when you first started on a certain node, in this case, node 1. Node 1, he has an ID, he has no current ensembles, and it is not enabled. On the other hand, if you go and enable it, you send an enable PID to the manager that runs the node. We end up basically setting enable to true, and we created an ensemble. This is the root ensemble. And so the root ensemble here is basically the leader of the cluster now, and he's the one who establishes all the other metadata. And so to do that, the manager, you basically, when he sees a state change, periodically sees this, he actually realizes, hey, there should be a root ensemble running now. The manager will see this whenever that state eventually propagates to that node. He will then add that to the peer supervisor. The peer supervisor will then spawn that up. So we actually dynamically add the peers that are part of these ensembles as part of the state as it gossips around. And then eventually, if you wanted to join nodes, you can only join nodes that are not enabled, because if you have two completely separate, consistent histories that aren't compatible, it doesn't make sense to join them together. And so there's a property here where the node has to be false, and you can join them to a node that is true. And to do a join, you basically send a request to this guy, who then sends his state to this guy, and who basically just wholly replaces it. And so both nodes now sort of have a consistent view of that state. And then after the fact, and in doing that, sort of see that, you basically start with 3 independent clusters, or 3 independent nodes, which, this one would be enabled, these wouldn't be. You call join, you sort of have one global cluster now. And you can add or remove nodes. If any of you are familiar with Riak and Core, which is what we use Riak, or ever use Riak, Riak has something very similar. You just start nodes up and then join them together later dynamically, rather than sort of at the get-go saying, here's my fixed membership. And I'm running out of time here, so I'm just going to go through this real quick. Basically, to create ensembles, you send a message to the root peer. This is the root built-in ensemble who's responsible to creating other ensembles. So we have to consistently create new ensembles. And so to do that, that's why we start with just a single root peer, but he can create other ensembles. So to send a request to him, he sends a request to this directory. This directory is actually the state that was part of the manager in the other slides. And it was just broken out here. It goes to the directory. The managers eventually see this. This is basically an ets table. That's why it's separate. They'll eventually see the ets tables change. They will then gossip around. Eventually, all the managers see that's been gossiped around. And then what they do here is they all spawn, via their peer supervisor, the new peers. In this case here, so they dynamically create these new peers. Each of these peers start out with the state saying, hey, here's my 3 peers now. But there's no leader. So what ends up happening is they do an election. And this guy eventually becomes elected the leader, and he's the new leader. And so you can dynamically create, hundreds of ensembles if you want, or few, and still up to your app to route to these ensembles. And that's basically it. The last slide is just this one. We also, again, support dynamically adding and removing members, and we do this via joint consensus. So if you read the RAF paper, it talks about joint consensus. And the idea here is basically you need to have an overlapping set of members. So you might have, for example, a foo we saw earlier. It had 3 nodes, A, B, C. Perhaps you add in 2 nodes, D and E, and remove node C. To actually do this consistently, you actually have to have a period of time where you overlap both memberships. So you first have ABC commit a view that is both of these. Then all future operations need to succeed in a quorum of both sides. Whoops, this side and this side. And then you eventually, what you do is you commit sort of the future view. And for this future view to commit, it has to get a quorum from both ABC and a quorum from BDE. And those are separate, could be separate quorums. But you have to see from both before this to succeed. And there's a nice proof of this in the RAF paper, sort of why you need to do that. And that's what we end up doing to do dynamic membership. What Riak Zookeeper does in their new stuff is somewhat similar to this, to joint consensus. And that's it. So again, this is Riak Ensemble, a paxos-based framework for this. And again, I didn't go into much detail of some of the API just because I tried to cram as much as I could into this doc. But there is docs that are in the process of being written that'll have all the nice, here's how you can actually build something on top of this, and hopefully code examples as well. And then of course, Riak itself serves as sort of the canonical example of how to do this if you were to look at that code base. And anyone who wants to stay around and ask questions rather than go and drink coffee, feel free to talk to me.